I'm Anant, and today we'll be discussing about an autoscaling solution that we have developed for Trino on Dataproc. The solution was co-developed by me, Anant, and Shikha, working with us for a customer in APAC. So let's listen to the story first. So this is a Singaporean customer, a multinational bank, one of the biggest ones in the region, who uses Trino for analysis purposes and mainly for interactive queries, sometimes batch queries, but it's aimed at the analysts who run ad hoc queries using Trino on a lot of the data warehousing solutions, which is a combination of Hadoop, PostgreSQL, Oracle SQL, and a bunch of other databases. Trino, as you know, is a distributed SQL engine that allows users to run SQL queries on top of heterogeneous data sources by allowing them a sort of federation. Think of this like BigQuery federation, but running on Dataproc or running on Hadoop. What the customer was looking for during the migration process is a cost optimum or a cost optimized mechanism of using Trino on their Dataproc. The biggest challenge was because the queries were interactive, they had peaks and troughs, huge peaks and huge troughs across the entire day, and it was not a constant loading on that cluster. And they wanted to optimize cost. What we ended up doing was a local application which runs on the master node of the Dataproc. It is a Java application which is always running. It is a multi-threaded Java application which runs on the compute engine, which is the master node of a Dataproc, which is also the Trino coordinator. So Trino has this nomenclature where the Trino coordinator is the master or the main node, and then there are workers. What we also made a design decision on is to use or scale up and down the secondary worker pool. So Dataproc has this very interesting feature of primary worker pool and secondary worker pool. Benefits of secondary worker pool are secondary worker pool machines do not host HDFS, which means taking them out does not impact HDFS performance at all. This way, customers who may be using HDFS can still continue to use our autoscaling solution without impacting their HDFS performance when the workers are added or removed. There won't be need to rebalance the HDFS or to handle situations when a worker may be turned off, which may contain some valuable pieces of information. So we designed this autoscaler to work purely on secondary worker pool. So it only scales up and down the secondary worker pool. Now, let's look at some of the implementation considerations of this solution. So the nuances that we had was, number one, we were capturing all the clusters using monitoring API. So the cloud monitoring API gives you all the cluster metrics like CPU utilization of individual workers, memory, thresholds, all of that metrics. But it is up to 2 minutes delayed. Second, cluster scaling was based on secondary workers, which allows us to not impact HDFS performance as well as use preemptive VMs by default, which can benefit both from cost perspective and, as I said, HDFS perspective. Third, custom autoscaler application that runs on coordinator of the Trino worker or Trino cluster, and the Dataproc inbuilt autoscaler should be disabled because otherwise the Dataproc autoscaler may spin up a worker in cases where we may have actually spin down. So we do not want this kind of actions to be happening across. We want, when the Trino autoscaler, our solution is working, we want the Dataproc autoscaler to be shut down or turned off. One key thing to keep in mind is, if a new worker is added to a cluster, Trino only assigns new jobs to that cluster. Existing jobs are not redistributed to increase throughput. Now, this is something which is configurable, but we haven't done any benchmarking about redistributing jobs because it's a very complex issue to handle. So bear in mind that the current solution, we do not take into consideration that existing jobs which may already be running on the cluster, they will not get reallocated or resharded to be sent to the new worker. So the new worker CPU utilization will only go up in situations where a new query comes in. It is scaling up proactively to make sure that if a new query comes in, that query gets the maximum possible throughput that is available. Now, looking into the exact algorithm, or let's say the flowchart of how our Trino autoscaler works. So let's start with the top of the chart from monitoring. At regular intervals, the application is running a polling timer. So it's a multi-threaded application. It is running a polling timer which is configurable. Based on the polling timer, it will pull the monitoring metrics from cloud monitoring. Then it will do an averaging or a windowing of the CPU metrics for every worker. Then it will calculate average utilization of memory and CPU. Currently, we have only designed it to work on CPU, but the system can be configured, or the feature can be very quickly added to work on memory as well. So it looks currently at the CPU utilization of the secondary workers, average CPU utilization. Then it makes a decision whether there was a rescaling done in the near past. So every rescaling will trigger a cooldown window, which is needed for the cluster to stabilize. So if it is within a cooldown period, no action will be taken. If it is not within the cooldown period, it will check whether the CPU utilization is between the upper threshold and the lower threshold. And if it is not, let's say the CPU utilization is above the upper threshold and the current cluster node count is less than the max number of nodes, that means that the cluster's utilization is going up and we need to add more workers into the cluster. It will call the Dataproc control plane and add more clusters, one secondary worker at a time. In another situation, if the CPU utilization is below the down threshold and the node count is higher than the minimum number of nodes that are required for the cluster, that requires the cluster to be downscaled. Now, this downscaling happens in a sequence of processes. It's not as easy as calling the Dataproc control plane and shutting down that secondary worker, which you can definitely do, but in which case one of the two things will happen. Either based on the configuration of Trino, either that entire Trino jobs or set of jobs that were running on the secondary worker will fail, or they will restart. Both of these scenarios are not ideal or not great from a cost as well as throughput perspective. So what we're doing is we're identifying the worker which has the least CPU utilization, and then we call the Trino's graceful shutdown endpoint on that specific worker. Then we wait for that worker to shut down. Once the worker gracefully shuts down, we call the Dataproc control plane API to remove that specific worker from the cluster. And as soon as step one in this, which is call Trino graceful shutdown for a worker, is triggered, we start the cooldown period. So this is how the flowchart or the algorithm of the autoscaler works. What I'll do now is take you through a demo. For the demo, we will go to this repository that we have created on GitHub and clone the repository first. So going to the repository, getting the coordinates, opening up a terminal, and then cloning it. So this will clone the repository. If you now go to that repository, you will see that there's a demo folder. Inside the demo folder, to deploy the demo, the only thing that you have to do is two things. First, look at there's a sample config file. So let's just modify the sample config file. So this is where you're writing out what is the algorithm, how many workers do we want to add, how many workers do we want to reduce, what is the upper threshold, what is the lower threshold. So for example, I can make the upper threshold to be 30% and the lower threshold to be 20%. And then I want the cooldown duration to be 5 minutes and the polling duration to be 2 minutes. Graceful shutdown again is fixed at 2 minutes. So let me just make this polling duration 1 minute. In a real world situation, you would not want to do that. Saving that, and then now the only next thing to do is Terraform init. So you basically initialize the Terraform. The Terraform is already pre-formatted. In case you want to change the region that you're deploying in, you can go modify variables.tf. And I have predefined the region to be US Central 1 and US Central 1A. In case you want to change it, you can go ahead and change it. For now, I'm going to keep it like that. So to deploy the demo, you just say Terraform apply. It is going to ask you about the project. I have a project named Anant the demo. So using this, it is going to now deploy the entire demo. For the purposes of demo, we are going to be using one of the BigQuery public datasets, which requires access to BigQuery. The GitHub repo talks about the entire configuration that you have there. And before getting into all of that, we'll now wait for the entire demo to get deployed. Okay, so the demo has actually got deployed. All the infra is deployed. You can see that 15 resources added. And what it is now showing you is a dashboard URL. So the Terraform also automatically generates a cloud monitoring dashboard for you to see how things are moving on. And it will also give you a command to connect to the Trino Dataproc cluster master system or the controller machine so that we can start running Trino workloads as a demo. So let me first click this and open the dashboard. So if you see, this is a cloud monitoring dashboard, which let me turn on auto updates. So you can see that the dashboard will now auto update on its own. So you'll see that it has captured some CPU metrics, a bunch of other things. Now what I'm going to do is I'm going to create a new tab and just copy this gcloud command so that I can SSH into my Trino master. So now I'm on my Trino master. For the cases of demo, I've already given out what is a set of commands to do next, which is connect to Trino first. So going here and connecting to Trino. This will connect to the Trino server locally and also load the BigQuery public dataset, which is the world population dataset. What I'm doing there is I'm running a very simple but very large query, which aggregates the population across a grid of map and then sort and groups it and orders it. So this is a fairly large calculation. What I'm going to do next is, again, I'm going to trigger the same query maybe 2 or 3 times so that I can simulate sufficiently large load. Then I'm going to copy the next command, which is the Trino. So connecting to Trino here, connecting to Trino here, connecting to Trino here, and then running the query, running the query, running the query, running the query. So now you can see that I'm running about 1, 2, 3, 4 queries simultaneously. So it takes about 2 to 2.5 minutes for the monitoring dashboard to update, but it is already now in auto refresh mode. So let's wait for maybe a minute and see how the dashboard is working. So now I am in the Trino Autoscaler, and you can see that there's a log file. So let me just do tail Trino Autoscaler.log, and you will see that the current average CPU utilization is just 24%. So it's still not crossed the upper threshold that we had configured for 30%. So I'm going to generate one more query so that it now crosses that threshold. So now let's look at the tail again. So now you see the average CPU utilization is 52, and it has decided to make an expand cluster. So when it is expanding the cluster, it's going to add 5 new workers to that cluster. So let's see if the dashboard updates quickly. So as we saw through the demo, I'm just putting in some sample metrics, some graphs that that we captured during some past runs. Put it into the slide, which you can then use for your cases if you need to. You can very easily see that workers are being spinned up, and as soon as the CPU utilization went below, new workers were marked to shut down, and after some time they were shut down. So the overall system worked fairly okay. Now for this particular demo, what I did was I changed the metrics to be very, very aggressive, which means that the scale up was happening at a very smaller threshold. Like it was going up as soon as the average CPU utilization went above 30%, and it aggressively scaled down as soon as the average CPU utilization went below 20%. This is not a real world example, because in a real world example, this will take a longer time to simulate and for me to demonstrate the actual scale up and scale down. So for the case of demo, I have actually tinkered the config to make it extremely aggressive so that it scales up fast and scales down fast as well. In a real world situation, we would want these to be quite big. For example, we do not want to scale up before the CPU threshold start hitting somewhere about 70%. And similarly, we do not want to start scaling down till the average CPU utilization goes below 40% or 30% maybe. So with that in mind, what I'll do is I'll leave you with further resources. You can contact Shikha or me. The solution is already open sourced on GitHub. We have published a blog post on Cloud Blog. Thank you so much. Happy to look forward to your questions.